Hello everyone, my name is Han. Today, I'm so happy to talk about one of my project here, and the topic is the semi-supervised learning in wearable-based momentary stress detection in the wild. First, I'd like to introduce some of the background to you guys. So why stress detection matters? Because, okay, thank you. Yeah, why stress matters? Because first, according to literature, stress can help some people's performance in some specific tasks. For example, but I'm not sure if this is true because I'm currently stressful right now. So, but we will see later. And I just read the literature. And another thing is, but exposure to long-term stress is usually harmful to people's health, including both mental health and physical health. If we can detect stress, it will be great because we can help people be aware of stress status, and we also have an opportunity to provide some interventions before those stress-related problems become very serious. So, my research is mainly focused on the wearable sensors, which has advantage compared to the like video image, because it's protect the participants' privacy. We don't have many other issues, right? And so a prototype of this kind of model is that first we will have data from wearable sensors, for example, heart rate, skin conductance, even ECG and accelerometers, etc. People usually build a machine learning model, so we can get stress labels. Those labels are usually self-reported by participants. But those kind of model has achieved some degree of success, and we also already see some promising results. Also, but if we want to improve this model, we want to improve something, then we also have a challenger, which is the label is actually sparse. As you can imagine that for the wearable sensors, even if it's just a function normally functioning, we will have over thousands of data points every day. It's very easy because we just need to participants warn the wearable sensors, and we don't need to do anything else. But for labels, as I mentioned before, it's self-reported, which means we need to send a survey questionnaire to participants every day and actually, hey, how are you feeling right now? Are you feeling stressed? So in this case, we usually only have less than 10 labels every day because we can't really send thousands of surveys to participants, right? Otherwise, they will probably just report us, about some study policies. In this case, some researchers try to align the label and with the data, which means we only keep those labeled information. And some other researchers try to downsample the data, which means we will calculate some of the high-level features using a preference window of the label timestamp, so that we can get some high-level features for that. But those two methods cause a loss of information because both, the first method omits or discard a lot of things, and the second downsampling is also triggers some loss of information. And nowadays, according to the developer in deep learning, we have a lot of time series learning, like R and also transformer, so that we can actually model a sequence of data and try to use a sequence of data to predict the stress. But the thing is still here, even we have a segment the data into sequences, we will still have some unlabeled sequences. The question is, will those unlabeled data be helpful? But if so, how can we use them? So I will introduce our method, which is we design a two-stage semi-supervised learning framework. First, I'd like to give an overview of a framework. We have two stages. The first stage is pre-training, which means we use an autoencoder structure and use an unlabeled data. And the second stage is fine-tune. We will use both labeled and unlabeled data. So in the second stage, we will also involve a concept of consistent regularization, which I will talk about it in the following slides. Here is a figure of autoencoder, which is purely the first stage. So imagine that we have an unlabeled sequence, and we have an autoencoder, which is formed by LSTM. We input the sequence and into LSTM to get some auto features, and we will use a decoder to recover the auto feature and get a reconstructed sequence. And the objective of this autoencoder is to try to recover the sequences, and we will make sure it as similar as possible. So the point is, even if we don't have a label for those unlabeled data, we don't know how what kind of stress it reflects to us, but we can still use the encoders to extract some useful information because it can at least recover the sequence back. And in the fine-tune part, if we can just transform those kind of parameters or weights then from the encoder, from the autoencoder, from the encoder of the unlabeled training, we will be able to inherit some of the information already learned from the unlabeled data. This is this is kind of a concept in the deep learning, and we will try to learn some useful representations. But whether are all the labels necessary to be put into the unlabeled data? Imagine that case. We have a labeled data and unlabeled data. Labeled data is usually corrected in daytime because participants cannot really report during their sleep, right? And also we have a lot of noise points. So which means not all the labeled data could be helpful in pre-training part. If we can see this figure, this shows a visualization of latent space representations. The blue one is the unlabeled representations, and the orange one is the labeled. As we can see in the figure, if compared to the unlabeled data, labeled one only occupied a small portion in the figure, which means if we just select the other part of the data, it might not have a similar contribution to labeled data, so that they might not be so helpful in help us to get some stress prediction. So in this study, we designed a Gaussian mixture model, which is I cluster the labeled data and so that we can fit a Gaussian mixture model. For those unlabeled data, I will test the likelihood of how likely the data is obeyed to the distribution. If they are not in a stem distribution, we won't use them. In this way, we can improve the model's training speed, which means we will make it more efficient. So here is the stage 1. And for stage 2, we are involving a consistent regularization. So imagine that we have a sequence. The example is actually from the all test data, and it's origin data. We can also do some data augmentation based on some time series data augmentation method, such as gentering, scaling, time wrapping, magnitude wrapping. They are for the magnitude and the temporal information of the sequences. And we can input in the model and get 2 predictions. So the question is whether those 2 predictions are equal. Because ideally, if a model is robust, if a model is robust enough, the 2 predictions should be equal because it should be robust to some reasonable amount of noises applying into the original signal. If not, then this is something we want to regularize. So if we break down into a loss function, we will see for fine-tuning stage, we will have of course, we will have a supervised loss, which is tell us whether the prediction is good or not. And also, we will have a consistent regularization loss on both the labeled and unlabeled data. So in this way, we will also be able to leverage unlabeled data during our fine-tune stage. Yeah, let's go to evaluation. I evaluated the method on 3 public data sets. They are all data collecting wearable sensors data and from data from in the wild, and they have stress labels. They all have some limited amount of labeled data, but a massive amount of unlabeled data. I'm doing cross-validation on participants in independent setting, which means we will put some participants in training and others in testing and doing cross-validation and report results. So if we first look at active sampling results, the x-axis represents the amount of data we selected, and the y-axis is the performance in everyone score. We can see here, the active sampling actually help the model to converge faster if we compare to random sampling. And when we select only a few amount of data, it can give us some better results. And interestingly, if we can see for a small data set, and for example, tails, in the middle way of the selecting, the performance of using active sampling is even higher than we use all the data. So according to the results, this is the evaluation results. The first, the upper three rows represent our baseline, which is a random baseline, and the baseline of LSTM, and the LSTM with the data augmentation only. And the lower three, the bottom three rows represent applying our method. We found that the method on top of data augmentation, a method of pre-training at stage 1 and stage 2 give us the best results. Also, the middle rows actually we try to reproduce some method, some state-of-the-art method. Those methods are very well applied, very proof in computer vision tasks. So we apply them and try to reproduce them to compare with our method. And we found that the proposed method, our method, actually give us some competitive results. So finally, I will draw a conclusion. In this project, we developed a semi-supervised learning framework and try to tackle and try to address the sparse label issue in the wearable sensors-based stress detection task. And the active sampling can help the semi-supervised learning to be more efficient. In the future, we are thinking about combining the semi data set together because we have many similar things. For example, for the similar wearable sensors and the similar labels. So we are thinking about maybe combining those branch marks together so that we can get more label data. And also, I was trying to train and evaluate our method on a larger population so that the results will be even solid. Yeah, that's all. Thank you.
Any questions?
This is fascinating. Those numbers, again, I'm not an expert. This slide, these 0.59, does that mean that the closer it is to 1, the better correlation?
Yeah.
So it's sort of flip of a coin in several cases.
Yeah, this task is actually kind of a challenger because all data is collected in wild and the participants doing some subjective reported data label, which actually very it's a very tough detail. It's a very tough and a challenger task, and so that we used a random guess baseline to try to say our model is actually even better, just a little bit better than the random guess by using an LSTM baseline. And actually, for the first data set, we launched a kind of a challenger. We launched a kind of competition, and the result is almost just below like 60% of an in F1 score. So this task is actually very challenging, but that's a good point. We still have a long way to go because the gap is from 0.6 and to 1, right?
It's great talk. Thank you.
Thank you.
Any other questions, final thoughts?
Thank you for the talk. I was wondering if you were able to use pre-trained ImageNet models that were pre-trained unsupervised.
Can you repeat your question again? Pre-training unsupervised?
Were you able to maybe start your model with a model that was pre-trained in a non-supervised manner on ImageNet? Would that be something helpful in your case when you want to start with a model?
Okay. Here? Do you mean pre-training by supervised model and
But the model is pre-trained in a non-supervised manner on
Yeah.
ImageNet.
Yeah, the pre-training is unsupervised right now.
Is that what you are using?
Can you speak a little bit louder? I can't really hear.
So the like the models that they use usually for data, they use pre-trained model on ImageNet dataset. So I was wondering if you could use a pre-trained model on ImageNet dataset.
Yeah. So in pre-training, we use unsupervised loss, and the model is, we actually use the transform the weights from encoder to the fine-tune part. So that is how we use unsupervised pre-training here.
Okay.
Yeah, thank you.
Okay, thank you.